So now we're going to study a thing called piecewise functions. Okay? Piecewise functions are given by this definition. So it's a function f that may have two or more expressions with a formula on different points of the domain, i.e. different x values. So when I'm talking about the x value, when I'm talking about this, it means I've got different functions for different sections of my graph. So we really need to spend a little bit of time on this today, so we're going to do all the questions we can. So let's say we had the graph fx is equal to the following: x squared for x being less than 0, but then x plus 1 for x being greater than or equal to 0. So now you're asking yourself, how would you draw something like this? So the key idea is to recognize that for certain parts of the graph, our graph looks differently, okay? Now, for the first part of our problem, it says it looks like x squared for x less than 0. So because that's the case, what we have to do for our graph is we have to put a dot at where x squared would equal 0. So in this case, if I put x is 0 into my equation, the y value is going to be 0. So 0, 0 is a point on my graph. So I'm going to put a circle there. Now, because it is a parabola, I would just have to figure out the points of the parabola. So in this case, start from the vertex, go over 1, up 1, over 1, up 3, and then over 1, up 5 steps. So that means our graph does this. For x being less than 0. For the graph x plus 1 squared. Sorry, for the second half of the graph, it's not x plus 1 squared. It looks like x plus 1, but our graph is greater than or equal to 0. So x plus 1 starts at x equals 1. So I'm going to put a circle, but like a filled in dot at this point. So I've got my filled in dot above, and then its slope is 1, and my graph looks like this. There we go. And that is our function f of x. Take a moment and copy that down. So now imagine if I have a function where I have 3 different parts. Remember, I said that the function could have 3 different sections. Sorry, 2 sections or more. So let's say we have f of x is equal to -1 for x being less than 0. But then the f of x is equal to 0 when our x is equal to 0. Okay? And then we could also have x plus 1 for x being greater than 0. Now you're probably wondering, how the heck what could this actually look like? So for this graph, maybe you need to see what the equation would have looked like using y equals. So for this first graph here, I would tell you that this is just y is equal to -1, but it says it's for x being less than 0. So what does that really mean, right? I mean, seriously, what does it really mean? It means that my graph is a horizontal line. So remember, for everything less than 0, my graph looks like -1. So at 0, I'm going to put a circle or a circle since we have here a less than sign for 0. So we're going to put a dot at y equals -1. So we put a circle. And then, so we're saying we cannot be on that point for this value, but then it looks like -1. So what I'm going to do is I'm just going to draw my line. Oops, can't draw. So we have our graph looking like that for x being less than 1. But then at x equals 0, we have 0. So that's actually the point 0, 0. So notice I'm filling in my dot. And so now for the last part of the graph, it's looking like this equation. Y is equal to x plus 1. And we can easily draw that. So we're going to fill. So notice, because it's greater than 0, we have to put a circle around the y-intercept of our graph, because this is our y-intercept based on y equals mx plus b. So now, once you've got that, we're going to go up 1 over 1, up 1 over 1, up 1 over 1 using our slope. And literally we get a graph that looks like this. So that's a weird looking graph. And it's kind of like, there's kind of like a step here. Just notice it. There is a step. And it's broken. And the graph is broken. And you've never seen stuff like that before. Okay? So we're going to talk about that so we understand how we use this in this course and the next. We call this a discontinuous graph, and I'll explain it to you in the next slide. All right, so we're going to talk about continuity. When you hear about the idea of a continuous graph, this is what it means. There are no holes in the graph, i.e., no breaks. So if you literally took your finger and moved across the graph, you wouldn't be able to lift your pen off the paper at any time during the graph when you move your hand across the graph. So an example of a continuous graph is something like this. I have my chart, and then here's my graph. If I drew this line and I never had to lift my pen off the paper at any time, this is continuous. So now, where do we have the concept of discontinuous points, right? So you're discontinuous if you have a hole. Discontinuous. So if you have a hole on your graph, you're discontinuous. So imagine you have a graph that looks like this. And then when you draw it, you end up with something like this and a hole. So you literally have to stop and draw the hole, i.e., the point doesn't exist at this point, x. So at x is 3, the function doesn't exist at that hole. You cannot find a y value for it. So the next type of discontinuity happens when we have a gap. So for example, a gap is discontinuous. So that can happen in many different ways. You could have that graph where you have a point here, you have a point above, and then you have an empty point below. If I was drawing this, I would follow my line up to here, but then I couldn't do that. I'd have to jump to this point, then jump to that point. So that forms a gap. Now, another type of gap that you would see is a thing called a vertical asymptote. So imagine if I had something that looked like this. A graph that has a dashed line that we never cross, and it's vertical. That looks like this. So if I have a dashed line, that dashed line indicates discontinuity, because in this case, maybe x is 3 for that discontinuity. The graph, if I actually took my pen and drew it, I'd go from here all the way up to here, but then I'd have to lift my pen and start from here and go to here. But I'd literally have to take my pen off of the paper to recognize that. So if I ever have to take my pen off the paper to draw another half of my graph or another third of my graph, then we know that it is discontinuous. So when we have the concept of discontinuity, that happens at holes in our graph and gaps in my graph. Or you could say vertical asymptotes. Now, here's a big hint. Remember those functions with denominators where x cannot equal something? That is why we use this, to be able to identify discontinuous graphs. So I'll show you an example. So imagine I have a graph with two vertical asymptotes here and here. There is one side of my graph, then maybe my graph does this, and then maybe my graph does this. The fact that I have those two vertical asymptotes tell me is that it's discontinuous. The vertical asymptotes, asymptotes tell us that this is discontinuous. That's it. So now I'm going to give you two problems so we can kind of graph them. So let's say we have a function that looks like this. F of x is equal to 2x plus 1 for x being less than -1, but x is greater, for x being greater than or equal to -1, we're going to have x squared. So the easy part of this graph will be the second half of this graph. So that's for this part here. Our graph is x squared for x being greater than or equal to 1. So because x is greater than or equal to 1, what we're going to do is we're going to fill in the vertex of our parabola. Then we'll go over 1, up 1, over 1, up 3, and then we will graph. So that's the right half of our parabola. Now, as an aside, if you have a problem figuring out which points you're going to use for your parabola, do the following. Create a table of values. So for x is equal to -3, we just plug it into our equation. and plug it into our equation for -2 and -1, and you get the following. So now the only issue is at -1, this is not included. Because remember when we were looking at our graph here, it was 2x plus 1, but it was because it was x is not equal to, but it is less than 1. So we'd have to actually draw a negative sign for that. Now, I want to make sure that for my first parabola, we need to understand that we are going all the way over to this point right here. So because it goes all the way over, it goes all the way to this part here for x is 1. So all we have to do is draw here and put a dot. Now that we have a dot, that's where our graph ends. For the second graph, we have to use these points that we have here. So at x is -1, we are at -1, but we have to put a hole. Then at -2, we are at -3 and -5, and we draw our line, and you could easily tell me that this is not continuous. And you could say that because there is a step or a gap between the two different graphs. So now our final question of the day is this. Suppose I have a graph that looks like this. So the first thing I'm going to ask you is, can you define the function, right? So for the last half of my graph, you have the following. If I look at this graph, I can determine that if I extend this line out, this is the line of the following. X plus 1, but because we don't include the value of -1 for x, we have to say x is less than -1. So it looks like x plus 1 for x being less than -1. So the next part, the middle part, so that's right here. Okay, that's actually a parabola. And what you can do is you can determine that this is just, it looks like x squared, but here's the problem. It has values for x being less than or equal to, because of the dot we have here, the filled in dot, we're going to say it's less than or equal to 1, but greater than or equal to -1. And that is what we have for x squared, right? And for the last graph on top, it's a horizontal graph, is it not? And it's a horizontal graph that if I extend it out here, it happens at y is equal to +4. So my equation for the right half of the graph is this. Y is equal to 4, but it's for x being greater than 1. And then you can say fx is equal to this set of functions. So now what we have to do is we have to state the discontinuities, if there are any. Now, the discontinuities for this one are the following. And this is how you answer it. You say the function is discontinuous at x equals -2 and 2, and we're done. So for your homework, you're going to do page 88. You're going to do number 1, 3, 5, 9, 11, 37, and 39.